Hey everybody, welcome to Algo Expert. In this video, we're going to be covering the construction of a binary search tree, which I'm going to be referring to as a BST from here on out. So a BST is basically a special type of binary tree, and a binary tree is just a data structure that consists of nodes where each node has a value. The value could be an integer value, a string, an array of values. Typically, it's going to be an integer value, though. And each node also optionally has two or up to two children nodes. And typically, these are going to be referred to as the left node and the right node. But so a BST is different because every node in a BST has to satisfy an additional property called the BST property. And so the BST property is defined as follows. It says that a node's value must be strictly greater than all of the values of the nodes to its right, or rather, sorry, to its left. And the value of a node must be less than or equal to all of the values of the nodes to its right. So let me repeat that, and I can show you in this example that we have right here in front of us. The node at the top, the root node that has the value 10, is a BST node or satisfies the BST property if and only if its value is strictly greater than all the values of the nodes to its left, so all of these values here, and its value is less than or equal to the values of all the nodes to its right here. And on top of that, for the BST property to hold, there needs to be one additional thing, which is that the left and the right children nodes of the node that you're looking at have to also themselves be BSTs and satisfy the BST property. And so that is the definition of a BST. Every node in the BST satisfies this special BST property. Now, I will note that the definition of the BST property can vary a tiny bit depending on whom you ask. The main difference is that some people will change the way they talk about the less than or equal to part. So here, for the sake of this video, we're defining the BST property as every node to the left has to be strictly less than, or has to have a value strictly less than the parent node, and every node to the right has to have a value greater than or equal to the current values node, or the current node's value. But some people will say, oh no, BST should not hold any duplicate values, and others will say you can put the duplicate values to the left of a node. But for the sake of this video, we'll go with the right side. So that is the definition of BST. Now, what do we mean when we say construction of a BST? Well, we're talking about a few methods that we want to support, or that we want our BST class to support. And these methods are going to be insertion, searching, and deletion. There are other functionalities that are typical of a BST, like traversals, but we're not going to be covering them in this video. In fact, if you're interested in those, you can definitely check out some of the other BST videos that we have right here on algoexpert.io, because we cover them there. But so the main methods that a BST absolutely must support are insertion, meaning if you want to insert a new node with a given value in the BST. Searching, you want to find whether or not a BST carries or contains a node or a value. And then removal or deletion, you want to delete a specific value from a BST. Now, these three methods are going to all follow a very similar logic, and they're going to take advantage of the BST property, which is why a BST is good in the first place, because these three methods can be implemented very optimally and can run very fast in terms of big O on a BST. but I will definitely say that deletion is the hardest of the three. In fact, deletion is a lot harder than insertion and searching, especially when it comes to the code implementation, just because there are a lot of sort of edge cases to take care of. With that being said, let's dive into it and let's start with insertion. So let's say that we want to insert the number 12. We want to insert the number 12 in this BST that we've got in front of us. So the first thing we're going to do, obviously, is call the insertion method on the BST, meaning on the root node. And from there, what happens is we start by comparing the value of the node that we're at, which is 10, to 12. So we're going to say, is 10 greater than or lesser than 12? Or is it equal to 12? In this case, 10 is smaller than 12. So what that tells us is that we want to insert 12 to the right of 10, because if you recall the definition of the BST property, every value that is greater than or equal to another value has to come to its right. So 12 has to be located to the right of 10. So what that means in practice is that we can actually eliminate this entire left subtree here that I'm circling. This entire part of the BST, we no longer need to explore because we know that 12 will not be located in it. And so now we can go further down the right subtree at this node that has the value 15. So let me erase this circle, and now we're looking at 15. So we compare the value 15 to 12. And we notice here that 15 is greater than 12. So what does that tell us? Well, it tells us that every value to the right of 15 is also greater than 12. And so we want 12 to be to the left of 15. So we can eliminate this entire right subtree here. We will never have to explore it again, or explore it at all. So now we go further down the tree to the left to this 13. And once again, we compare the number 13 to 12. And we notice that 12 is smaller than 13. So what does that tell us? Well, it tells us that we can eliminate this entire right subtree. We never have to explore it. And so we go further down the tree, and here we notice that there's nothing here, right? This particular connection here points to the null value or the none value. We're at the end of our tree. So we can insert the number 12 here. That's where the number 12 belongs. And so if we grab this number 12, we can move it down here in its position. And we've successfully inserted the number 12 in the BST. So the important sort of logic to recognize here is this idea of eliminating half of the BST at every node that you traverse or that you explore. We started at the root node, and by realizing very simply that 12 was greater than 10, and that therefore 12 had to be in the right subtree of 10, we eliminated an entire half of the BST. And then similarly, we eliminated an entire half of the remaining BST because 12 was smaller than 15. And then we eliminated another half of the BST because 12 was smaller than 13. And finally, we found the correct location. And that is the beauty of a BST, is that it allows us, for most of these methods, to only explore half and half and half and half of all the sort of BSTs and sub-BSTs within it. And so now, if we move on to searching, let me undo all of these circles. If we move on to searching, because this is basically the bulk of insertion, we've successfully implemented insertion and kind of explained how the algorithm conceptually works. Now, if we go on to searching, we're going to notice that the logic is very similar. So let's say that we were searching for the number 12 again. We start at the top, right? We call the searching method on the BST, so on the root node. What do we want to do? Well, just like we did with insertion, we compare the value of our node, which is 10, to the value 12. And so we notice that 10 is smaller than 12. Therefore, if 12 is contained in this BST, it will have to be to the right of 12. If 12 is located to the left of 10, or to the right of 10, sorry. And if 12 is located to the left of 10, then we're not dealing with a BST. But here we are assured that we are given a BST, so 12 must be to the right of 10. And once again, we can kind of eliminate this entire left subtree. So now we move on here. We compare 15 to 12. This should ring a bell because this is literally identical to what we did with insertion. 15 is greater than 12, therefore we eliminate this entire right subtree. Now we move on to 13. 13 is greater than 12, so we eliminate this entire right subtree. And then finally we get to 12, and 12 is equal to 12. That's the value we have found it. Now, if, let's say we were looking for, instead of 12, let's say we were looking for 11, we would have gotten all the way to this 12 here. And then we'd say, okay, 12 is greater than 11. So let's look to the left of 12. And here, there's nothing here, right? We're at the end of our tree. We don't have the none. We have the none value or the null value, but there are no more nodes. So at this point, we can just return false and say, oh, we didn't find the number 11, and we can guarantee that it is not in this BST. But so that is how searching works conceptually. And once again, it's exceedingly similar to insertion. So now we're left with deletion, right? The removal of a node, the removal of a specific value. And this is going to be a lot tougher. It's still going to use the same logic of comparing the current node's value to the value that we're trying to delete, and eliminating all the subtrees. But there are a few edge cases we have to take care of. So the simplest case here is, let's say we wanted to remove the number 1, okay? 1 here so happens to be a leaf. So first of all, how would we figure out that 1 is a leaf? Well, we would start at 10. We would see that 10 is greater than 1, so we would eliminate the entire right subtree. So then we would move down to 5. We'd see that 5 is greater than 1. So we would eliminate this entire, let me put in purple, this entire right subtree. And then we would eliminate this entire right subtree. And finally, we would be at the one that we're looking for. So in a way, you can think of the removal method as first searching for the value. If you never find it, then you never have to do anything. But if you do find it, then you remove it and you have to do some additional functionality. And so what happens when you do find it, right? So you get to this 1, and 1 is equal to 1. You want to remove it. This is the easy case because this 1 node here doesn't have any children nodes. So literally all we have to do is kind of like erase it, right? And have, this be null. So the left child of this 2 here is just going to be null. Basically, for the conceptual overview here, we can just erase this entire arm. Similarly, so that's an easy case, right? And similarly, another easy case is, what if we wanted to delete 2 instead of 1? So let's write 2 here. If we wanted to delete 2, we notice that 2 here only has 1 child node, which is this 1. So all that we have to do, theoretically, is grab this 2 and move it and kind of erase it. And then grab the 1 and connect it to the 5, right? And once we do that, we're back to having a valid BST, and we've effectively removed the 2. And this is the same thing if we have, if we were dealing with a 2 here that only had a right child node, so let's say it had like a 3, this would be the exact same thing. We'd erase the 2, and then we would grab the 3 and connect it here. And we would have a valid BST. So these are all the easy cases. But now the hard case happens when you want to remove a node that has 2, fully non-null children nodes. So let's say that we wanted to remove the number 10, which happens to be the root node here. So if you want to remove the number 10 here, you can't just erase it, because what happens now? What node do you put here to replace it? You can't move the 5, for instance, because if you move the 5, then what do you have here as the left child of 5, right? 5 also has 2 children nodes, and you can't just grab this entire tree and move it up here. Like, this just doesn't work. So there's a technique to this. What you do is, when you find the node that you want to delete, in this case 10, we found it immediately because it's the root node, you grab the smallest value in the right subtree of that node. Okay? So I'll repeat this. You grab the smallest value in the right subtree of that node. In other words, you grab the leftmost value in the right subtree of that node. So here we're at 10. We look at the right subtree, which starts at 15. What is the smallest value in this right subtree? What is the leftmost value in this right subtree? It's 12, the one that we added earlier. So we traverse this right subtree and find the 12. And what we do is we grab the 12, or rather we grab the 12's value. So let's write here, we write 12. We keep track of that value. We erase our 10, because our 10, we want to delete it. And we replace the 10 with 12. So we literally replace the value that we're deleting, or the node that we're deleting, we replace its value with the smallest value from the right subtree, which is 12. Okay? Why do we do that? Well, because this 12, we know that it can come in this position. The 12 was located to the right of 10, meaning that it was greater than 10, and it was, or greater than or equal to 10, and by sort of transitivity, it was greater than or equal to, or not greater than or equal to, it was strictly greater than all of the values here that were to the left of 10. Because any value that is in the right subtree here must be greater than all of the left values, since it has to be greater than or equal to the value at the top. But similarly, because this 12 here was the leftmost value of the right subtree, and it was the smallest value, we know that it's smaller than all the values above it. It's smaller than 13, it's smaller than 15, smaller than 14, than 22, so it's fine to put it here. So you see, the idea is that the smallest and leftmost value of the right subtree is the only value that can fit here 100% for sure. And also, it's the easiest value to put here because now we want to delete it in its other place. So what we're going to do is we're going to go down where we found it and erase it. And because it's at the very bottom of the tree, because it's the smallest value of the right subtree, it's one of the easy cases to delete, where we just have to replace it with null. And just like that, we've removed 10 from the BST. And we haven't removed 12, right? We just moved 12 up here. So let's reiterate what we did. Let me erase this 12 and let me rewrite 10 because I want to make sure that this is very clear. We want to remove the number 10. First, we have to find 10. We found it here. It's at the top. And we notice that 10 has both a left child and a right child. So we can't easily remove it. So what we do is we find the smallest value in the right subtree. So we go to the right subtree and then we go all the way to the left. It happens to be 12. We write down 12 just so that we keep track of it. We replace the 10 value with 12. And then we kind of call the remove method on the 12. So we go down in our subtree, find where we had the 12, and erase it very easily because this is one of the easy edge cases where the node doesn't have any children nodes. And we're done. That is removal. So you can see how removal uses the same logic as insertion and deletion in that we do these comparisons of the values. But it is a bit more involved, especially in terms of code. When we get into the code, it's going to be even more complicated than the conceptual overview, just because there's kind of a lot to write. You'll see it'll make a lot more sense when we do it. But overall, it's not that difficult once you get the hang of it. Now, let's cover the space-time complexity analysis before we get into the code walkthrough. In terms of time and space, we're going to be dealing with an average case and a worst case scenario, okay? So the average case, and I'll explain what I mean by that in a second, the average case here is going to have a time complexity of O of log of n. And this time complexity is going to be the same for insertion, searching, and deletion. So all three are going to have O of log of n time, where n is the number of nodes in our BST. Why is it O of log of n? Well, recall that when we were inserting, searching, or deleting, we didn't traverse the entire tree. We didn't iterate through the entire BST. At every node that we explored, we eliminated half of the tree, half of the remaining BST. So we started by eliminating half, then we eliminated another half, then a third half. And every time, by eliminating half and half and half and making the amount of nodes that we have to explore smaller and smaller and smaller, that leads us to a time complexity of O of log of n. Now, the reason this is only the average case, as opposed to the worst case, which I'll write below here, the worst case is going to be time equals O of n. The reason this is only the average case is because, unfortunately, there are some cases where this logic and this sort of advantage of being able to eliminate half of the BST isn't possible. And so what I mean by that is, imagine our tree had been this. It had been 10, 12, 13, 15, 22, and then 33. This tree here, this is a tree, right? The only difference is that there's only one branch in this tree because every single node is greater than its parent node. So there are never any left nodes. But so for a tree like this, because there are never any left nodes, you're never really eliminating half the tree, right? If let's say you're looking for the number 34, which doesn't happen to be in the tree, you start at 10, then you look at 12, then 13, then 15. Every time you're eliminating the left part of the tree, but there is no left part. And so because of that, you are actually exploring the entire tree, and that runs in O of n time. But that's the worst case, because on average, the tree is going to be kind of balanced, like the tree that we dealt with here, which is sort of balanced, meaning it has the same amount of nodes to the left as to the right. And in the average case, you are going to be eliminating half the tree, and so you're going to be running an O of log of n. And like I said, this is the same for insertion, searching, and deletion because they all follow the same kind of logic. Now, In terms of space, space is a bit more tricky. The reason space is tricky is because there are two different versions of the space analysis. One version, if you implement your algorithms recursively, is going to run in O of log of n, just like the time on average, and O of n in the worst case. So, like I said, this space complexity here, or these space complexities, occur if you implement your algorithm recursively. The reason being is if you implement your algorithm recursively, you are effectively using up frames on the call stack. So what I mean by that is if you're implementing your algorithm recursively, let's say you're doing the searching method, you call the searching method on the root node, which is 12 here, and let's say you're searching for the number 14. You call it on the number 12, and 12 is less than 14. So then you call the searching method on the number 15, and you're using up a frame on the call stack from when you called the searching method on 12, right? So like if you have your call stack here as like a big bucket here, you first have the searching method on the node that has the value 12. Then you have it on the node that has the value 15. Then you call it on the node that has the value 13. And finally, you call it on the node that has the value 14. And it's only at this point that you can start erasing frames and clearing frames on the call stack. But so that means that there is a point where the maximum memory usage is all of this branch, right, on the call stack. And what does that equate to? O of log of n time, or O of log of n space. Similarly, you could call this O of d space, where d is the depth or the height of the BST, meaning the length of its longest branch. And similarly, just like with time, in the worst case, this is going to be O of n, because if you have a tree that only consists of one branch, then you are effectively storing on the call stack n or n minus 1 frames, because you're going through the entire branch. Now, the reason I said that space is a bit more complex is because you can actually solve all of these algorithms, or implement all of these algorithms, iteratively, not recursively. And if you do them iteratively, then this space complexity changes to O of 1 space, constant space. And that's kind of the beauty of iteration versus recursion. Oftentimes, iterative implementations will be better from a space point of view because you will not be using or storing frames on the call stack. But anyway, that is it for the conceptual overview of these of the BST construction of all these methods. Now we will dive into the code walkthrough to see what they look like and to see if we can make sense of it all. All right, so we've got our BST class defined. Every node has a value, has a left and a right node. Both of these are defaulted to none, or the null value. And then we've got our insert, contains, and remove methods. And they all take in a value as a parameter. The remove method is also going to have an optional parent node value or argument, which we'll talk about in a little bit. But so let's start with the insert method. So we're going to be implementing these algorithms iteratively, since the iterative solutions are better from a space complexity point of view. That being said, we do have the recursive solutions on the algoexpert.io website, so definitely check them out in the editor above. Now, let's dive into this iterative solution for insertion. The first thing we want to do is initialize a variable that's going to allow us to keep track of what the current node is. What node are we at? Because when we call this insertion method, we call it on the root node of the BST. But then we start traversing the BST and we want to keep track of where we're at. So we're going to say current node is going to be initialized to be self. Because at the beginning, the current node is the node that we called the insertion method on, and that's self. And so then we can say while true, so forever, right? Until we use a break statement or a return statement, we do what's in this while loop. If the value of the value that we're trying to insert is less than the current node's value, then we know we want to explore the left, right? The left subtree. If the value is greater than or equal to the current node's value, then we want to explore the right subtree. So what we're doing here is we're doing this comparison, right? The comparison of the current node's value to the value that we're trying to insert. But so now, if we're looking at the left subtree, because the value here is smaller than the current node's value, then what we want to say is, let's check if the left node is an actual BST, or if we're at the end of the branch, right? So we're going to say if current node dot left is none, meaning we're at the very end of a branch, then current node dot left is going to be equal to a new BST that takes in the value that we're trying to add. And now we've effectively inserted the value in our original BST. And here at this point, we can break. Then else, if the current node dot left is not none, meaning we still have a left subtree to explore, then we can say current node is going to be equal to current node dot left. So we assign our current node to now be equal to the left subtree. And similarly, the logic for the right subtree is going to be identical, right? So if the value that we're trying to insert is greater than or equal to the current node's value, then we check if the right subtree is none. If it is, then we assign it to be BST, taking in the value that we're trying to insert, and we break out of this. And otherwise, we can assign the current node to be equal to current node dot right. And that's it. That is our insertion method. And then at the end, we can return self. This is just because this is going to allow us to call the insert function kind of one after the other during test cases, so that we can do something along the lines of test bst dot insert 1 dot insert 5, so that we can kind of chain these calls of dot insert. But overall, this return statement here is not really relevant to the algorithm. So this is going to run on average in, so the average case is going to run in O of log of n time and O of 1 space, because of the fact that we're implementing this iteratively, and we never call the function recursively, and the only thing that we keep store of is the current node, which is constant space. And then in the worst case, it's going to be O of n time and O of 1 space still. All right, so now let's move on to contains, the searching algorithm. So the searching algorithm is going to be very similar to insertion. It's going to be even simpler. We start by initializing the current node to be self, and then we say while the current node is not none. Let me give myself a bit of room here. So while the current node is not none, we check, right? We compare the values. So we say if value is less than current node dot value, then current node is going to be equal to the left subtree, current node dot left. Else, current node is going to be equal to current node dot right. And here actually, we don't do else, right? We do elif. So else if the value is strictly greater than current node dot value, only in this case do we explore the right subtree. Because if we are in the case where the value is equal to the current node's value, then we're done, right? We found the value, so our BST contains the value, and we can just return true in this case. So again, the difference here between the insertion and the contains methods is that for insertion, we only do if it's less than, do something, otherwise do something else. Explore the right subtree. Here, If it's less than, explore the left. If it's greater than, explore the right. Otherwise, we've found the value, return true. And then otherwise, if we ever get to a point where the current node is equal to none and we break out of this while loop, then we return false, because that means that the node is not contained in the BST. And this, similar to the insertion method, is going to run on average in O of log of n time, O of one space, at the worst, O of n time, O of one space. All right, now we get to the removal method, sort of bread and butter of BST construction. And this is the difficult method because it's got quite a few edge cases, okay? The first thing we do is declare the current node and initialize it to be self, same as the others. And then again, we say while the current node is not none, we can do some stuff, right? We can start comparing values. Basically, it's as I said in the conceptual overview, you can think of removal as a two-step process. First, you find the node that you're trying to remove, right? Or you find the value that you're trying to remove. And then you actually remove it. So while the current node is not none, if the value is less than current node.value, so the value that you're trying to remove is less than current node.value, then you set the current node to be equal to current node.left. And here, an additional thing that you can do is you want to keep track of the parent node. The reason we're going to want to keep track of this parent node, and that's why I added it as an optional parameter here that gets defaulted to none, because when you call the remove method on the root node of the BST, there is no parent node. But that's because when we are going to remove a node, we're going to want to kind of reassign the child node of the parent of the node that we're removing. So we have to keep track of the parent node. And so here we can say parent node is going to be equal to current node. Because when we update the current node, the parent node becomes the node that we were just exploring. And so here, similarly, we can say if value is greater than current node.value, right? Then parent node is going to be equal to current node again, and current node is going to be equal to current node.right, because now we're exploring the right subtree. And now we get into the actual bread and butter of this algorithm and of this method, which is the else case, right? The case where we have found our node and the value of the current node is equal to the value that we're trying to remove. So what happens here? Well, within this case, there are quite a few subcases, right? The first subcase is the one where we're dealing with a node that has two children nodes. Like when we tried to remove the root node, the value 10, and it had two children nodes. Well, in that case, as we said, we want to find the rightmost value, or sorry, the smallest value of the right subtree, and replace it with the value that we're trying to remove, right? Like replace the value that we're removing with that smallest value, and then remove that smallest value. So that can be the first case that we deal with, right? We can say if current node.left is not none, and current node.right is not none. So if both of the children nodes aren't null values or none values, then the current node.value is going to be set to current node.getMinValue. And here, or sorry, current node.right.getMinValue. And here we're going to create a new method which is going to get the smallest value of a given BST. And here we're calling this on the right BST. Because as I said in the conceptual overview, we're looking for the smallest, leftmost value of the right subtree. And so once we found that, what we can do is we can remove that node. So we can say remove current node.right.remove. So call the remove function on the current node.value, passing in current node as a parent. So what's happening here? Well, here we've set the current node value to be the smallest value, right? So we can write current node dot value is equal to smallest value of right subtree, right? And so now we want to remove the smallest value of right subtree from where we got it from. So we can say current node dot right dot remove, pass in the current node's value, which is the smallest value, and pass in as a parent node our current node. Because remember, we always want to keep track of the parent node. And now that we're calling the remove method on current node.write, we don't want the parent node to default to none. The parent node should be the current node. So that is this edge case where we have two child nodes present. Now, the other case is when we don't have two child nodes present, right? And so in that case, there are again two subcases. There is the easy subcases where we're dealing with a node that has a parent node, and when we're dealing with a node that doesn't have a parent node. And what that means is, in other words, if the node that we're trying to remove is the root node of the BST, like the one that we did in the example where we removed 10, that's annoying because we don't have a parent node, right? The 10, the root node, doesn't have a parent node, so we have to do things a bit more complicated. Because here we can do something like to get, I guess, let me make this clear. Here, we're gonna come back to this case, or to the root node case. But if we're not dealing with the root node, and again, if this is confusing right now, I'm going to make this clear in a second. But if we're not dealing with the root node, we can say elif parent node dot left is equal to current node. So if we're at a point, we're at a node that doesn't have two children nodes, right? So we already dealt with the edge case where we have two children nodes. So if we're at a node that has either only one child node or none, then we check, is our current node itself a left child or a right child? If it is a left child, meaning that the parent node dot left is equal to our current node, well then in that case we just say parent node dot left is going to be equal to current node dot left if current node dot left is not none, else current node dot right. What does that mean? What are we doing here? Well, we're saying we know that our current node is the left child of its parent node, so we checked for this equality. Therefore, and by the way, this should be here. This should be indented, this elif. But so, therefore, the parent node dot left is going to be reassigned to either the left child node of our current node, if it has a left child node, so if current left is not none, otherwise the right child node. Okay? So like, if our tree were something like this, I guess let me write very quickly a tree. Let's say that we had 5, and this 5 here was pointing to the 5 was pointing to a 3, and then the 3 was pointing to a 4, and we were removing this 3, we would say, okay, 3 is the left child of 5, so we want to reassign the left child of 5 to be either the left node of 3 if it has a left node, but it doesn't. Therefore, we reassign it to the right node of 3, which could either be 4 or this could be none, right? And either way, that's fine. And so we reassign the 3 to 4 or to none. And so that's what we're doing here with this line. And similarly, we can say elif parent node dot right is equal to current node. Then we say parent node dot right is going to be equal to current node dot left if current node dot left is not none, else current node dot right. So the same logic, except this time we're assigning the right child of the parent nodes. Now, finally, we get to this case. And this case is the case of the root node. Why is it a special case? Because the root node doesn't have a parent node. And so, because the root node doesn't have a parent node, we can't just implement this in a one-liner where we reassign one of the child nodes of the parent node. So here what we have to say is elif parent node is none. So if we're dealing with the root node that doesn't have a parent node, if the current node dot left is not none, so if the child, because remember, we've already dealt with the edge case where our current node has two children nodes. So here we know that our current node only has one child node. If that child node is the left node, then current node dot value is going to be equal to current node dot left dot value. Current node dot left, or dot right rather, is going to be current node dot left dot right. And then current node dot left is going to be equal to current node dot left dot left. So what are we doing here? We're literally manually replacing all of the values and left and right nodes of our current node with the left node's values. And similarly, we can say elif current node dot right is not none. Then current node dot value is going to be equal to current node dot right dot value. Current node dot left is going to be equal to current node dot right dot left. And lastly, current node dot right is going to be equal to current node dot right dot right. And obviously, as you can tell here, we're doing this in a special order. Like when we were assigning when we were assigning stuff to current node dot left stuff, we want to make sure that we assign current node dot left last, so as to not overwrite current node dot left before we stop needing it. And similarly here, we assign current node dot right last because we need current node dot right for the other stuff. Now we're almost done. The last sort of edge case here, else, is if imagine we want to remove the root node that doesn't have any parent nodes, and on top of that, this root node doesn't have any children nodes. So if it doesn't have any children nodes, this is kind of like an edge case that you have to discuss with your interviewer. It's a really almost banal edge case because you're essentially deleting the BST, right? If the BST only has one node, the root node, that doesn't have any child nodes, and you're trying to delete that value, there's nothing you can really do, right? You can just like disregard it, or here, we can just say current node dot value is going to be equal to none. But overall, there's not much you can do here. It's just a mega edge case, and it's something worth discussing with your interviewer. Now, what is important to say here is that we want to add a break statement here. If we ever hit this point here where the value that we're trying to remove, we found that value, then we want to make sure to break at the end of all of these if statements. And that's that, right? That now we get out of this while loop, and here we can return self again just because this helps when we want to call the remove method and chain it, but this isn't really related to the algorithm. So that is the removal method. Now I just realized that we forgot to implement this getMinValue function. So we can do that now. The getMinValue function is going to take in just self, because it doesn't take in a value. And what we're going to do is, remember, we called the getMinValue on the right subtree. So we can just say, okay, current node is going to be equal to self. We use that same sort of logic of keeping track of the current node. And then while current node dot left is not none, just reassign current node to be equal to current node dot left. And then finally return current node dot value. So when we call here the getMinValue function, we say current node dot value equals current node dot right dot getMinValue. We just traverse the tree here, go all the way to the left, keep going to the left until we reach a none value, or until we reach a node whose left node is a none value, and then we return that current node's value. And so this is going to run just like the other two methods in of log of n time on average, of one space on average, O of n time in the worst case, and O of one space in the worst case. This is because we implemented this iteratively, so we have no space usage. So I hope this video is informative. I hope it was helpful. BS key construction is not necessarily easy. I mean, insertion and contain and searching become fairly straightforward once you understand how the sort of, logic of comparing values works. The removal method, on the other hand, is definitely a lot more involved and a lot more complicated, but it's definitely worth knowing. And that's that. I hope this video was helpful again, and I'll see you in the next one.